never increases. What values of k could be here such that it never increases? And so what it's saying is basically the first derivative, f dash x, is purely greater than 0. So let's find f dash x. A good start is u and v, which is x plus k and x squared plus k. U dash is 1, v dash is 2x. And therefore f dash x is u dash v, x squared plus k, take v dash u, which is 2x squared plus 2xk, over v squared. And if we were going to simplify that a step further, the negative jumps in everywhere, and what we're left with is minus x squared minus 2xk plus k over x squared plus k squared. Then you're being asked, for what values of k is this purely positive?
Negative? Negative.
Never increasing. Purely negative. Yeah. Never increasing. Why didn't you guys correct me? It's not greater than 0. It's less than 0. They could equally ask the question the other way around, but negative. What values is this negative? If this is negative, and it's a fraction, you need the signs to be different. The bottom is always positive. Anything squared will be positive. So the bottom of this fraction is always positive. For this to always be negative, the top is always negative. So what the question's really asking is, for what values of k is the top negative? So it boils down to, when is x squared take 2xk plus k negative? Now, in my year 11 class, I'm about to do discriminant and use of discriminant. There's a negative at the front.
Yes.
Thank you. And this is fundamentally a quadratic, and it's asking for what values of k is it negative. So it's a quadratic here with a negative at the front, meaning it's concave down. So we could conceivably imagine the quadratic to look something like this. If it looked like that, that would imply that, and remember this is effectively the sign of the first derivative. It would mean that it would be negative in some parts, positive in some parts, negative in some parts, so it would change. We're hunting the values of k for which it's purely negative. We want it to be something like that. For that to be true, the discriminant must be negative. So b squared take 4ac is less than 0, and we sub those values in. Minus 2k squared take 4 dot a dot c is less than 0. 4k squared plus 4k is less than 0. Factor out 4k. And then there are sort of another quadratic. You can see that it's equal to 0, and k is 0 and k is minus 1. So when k is 0, why did I do that there? 0 and minus 1, and you've got to think about what sign you're having here. So the signs are, if you put in minus 2 to both of that, they're both negative, so it's positive. If you put in 1 to there and there, it's positive, it's negative. And it's this section here that we're really interested in, because when k is between minus 1 and 0, the discriminant's negative. When the discriminant's negative, this quadratic is purely negative. When the quadratic's purely negative, the first discriminant's purely negative, so therefore it never increases. But we're going back quite a long way into our sort of maths box here to remember discriminant and quadratics. but that's why I think this one trips up many people. Your answer is, what values could k have? K is anywhere between -1 and 0, but not equal to. That's our final answer.
That's not the answer of the book.
Something else on the book?
Yeah, the answer of the book is -1 smaller or equal to k and smaller than 1.
So these sections here.
Yeah, include -1 and not include 1.
Include -1.
And not include 1. So from -1 to 1.
If it was
include
-1, wouldn't it equal 0?
If it was -1, it would equal 0. And if the discriminant equals 0, it means there's a repeated solution, which would mean that, that's a good technicality,
It's equal to increasing and decreasing.
which is increasing and
So
decreasing.
that counts.
Yeah, it does count, doesn't it? We'll pay that. I don't know where they're getting that 1 from.
I'm not sure.
I don't think they've got that right. I think it's 0, but we can pay the equal to, because then it's increasing and decreasing when it turns, which implies flat bits. Yeah. No, I think they're wrong, because that is smooth enough out. While I have your attention, I thought I'd do one from the next section as well. From memory, last year lots of people got stuck on it, so I thought we would have a run at it here. Prove ln x on x is less than or equal to 1 on e for all x greater than 0. So it's in the section where we're finding minimum maximum, and then we need to prove that the function is strictly below this point. What it's kind of asking us to do is to find the maximum value of this. If the maximum value of this is less than or equal to that, then we've effectively done what we've been asked to do, is show that this is below that for all values. So, we're finding the max of that. Good place to start is u and v. We have ln x on x, and therefore, I've copied what you guys do. Sorry, I hate that setup. U, V, because it does my head in for the next bit. U dash, V dash. Then, if we differentiate it out, U dash V is 1 minus ln x over x squared. Alright, and if that's the first derivative, we're looking for when it equals to 0. So 1 take ln x on x squared equals 0 occurs when 1 take ln x equals 0, which is where 1 equals ln x, where x equals e to the 1. So there is a stationary point at x equals e to the 1 because e to the 0 there. And it's the only solution. X, f dash x. I would sub points in both sides. So you can sub in, you can't sub in 0, but you can sub in the number 1. The number 1 is less than e. So if you subbed in the number 1, what's ln of 1? 0. 1 over 1 is positive. If you sub in, you can sub in the number 3. I'd probably sub in e squared, just because it makes the next bit nice. If you subbed in e squared, what's the ln of e squared? 2. So that's 1 minus 2 is negative 1 over e squared squared, but e squared squared is positive, so it's negative 1 over something positive. This is negative. So we've established there is a max at e to the 1. Does that make a little sense? So there's a max where x equals e to the 1. The question is, how high is that max? So there's sort of max at x equals e to the 1, or just e. We put that into the function, so we want to be finding f of e, and f of e is ln e on e. ln E is 1 and E. So that means there is a maximum when x equals E and the maximum height is 1 on E, which lines up with what they've said. This function is purely below 1 on E because it has a maximum at 1 on E. Does that vaguely make some sense? So it's a strange wording of it, but if you're asked to prove something is below something, just find its maximums or find its minimums and then compare it with what they've asked you to compare it with. That would be the answer. Alright, are you guys happy if I let you work on the remainder of 3B and start on 3C for a little bit, and then do you guys want to do another set of content drawing stuff today? Yeah, it's nice and early in the day, it's a good one to do on. So keep going with 3B and C, and then I will give you the next bit in a second. And this is now rather superfluous. Because you're right here. Hi.